Download this code from codegive.com, link in the description below. Job sequencing with deadlines, a comprehensive guide, cs402 level. This tutorial provides a detailed explanation of the job sequencing with deadlines problem, including its problem statement, greedy algorithm solution, complexity analysis, and a C++ code implementation. This is a common topic in algorithms and data structures courses, often encountered in cs402 level curricula. 1. Problem statement. You are given a set of n jobs. Each job I has profit, p sub I /sub the amount of profit earned if the job is completed. Deadline, d sub I /sub the latest time by which the job must be completed. Each job takes exactly 1 unit of time to complete. The goal is to select a subset of jobs to maximize the total profit, subject to the constraint that each selected job must be completed by its deadline, and no 2 jobs can be scheduled at the same time. Essentially, you need to schedule jobs such that you maximize profit without any job overlapping and each job being completed before its deadline. Example *. Job profit, p sub I /sub, deadline, d sub I /sub. --. 102. 210 315 427 583. The optimal solution is to select jobs 1, 3, and 5, resulting in a total profit of 100 plus 15 plus 8 equals 123. We can schedule them in the sequence: job 2, time 1, job 1, time 2, job 5, time 3. 2. Greedy algorithm approach. The job sequencing problem with deadlines can be efficiently solved using a greedy approach. The key idea is to prioritize jobs with higher profits and schedule them as late as possible without violating their deadlines. Algorithm steps *. 1. Sort *. The jobs in descending order of their profits. 2. Initialization *. Create a schedule array, or Boolean array, to represent time slots, initialized to false, or 0, indicating that no job is scheduled in that slot. The size of this array will be equal to the maximum deadline among all jobs. Initialize the total profit to 0. 3. Iteration *. Iterate through the sorted jobs. For each job, iterate backwards from its deadline, d sub I /sub, down to 1. If a time slot is available, i.e., schedule j equals false, schedule the job in that slot, set schedule j equals true, add the job's profit to the total profit, and break out of the inner loop. For result the total profit is the maximum profit achievable, and the schedule indicates which jobs are selected. Why does this greedy approach work? The greedy approach works because it makes the locally optimal choice at each step, selecting the job with the highest profit that can still be scheduled. By sorting the jobs in descending order of profit, we ensure that the most valuable jobs are considered first. Scheduling them as late as possible frees up earlier slots for potentially other highly profitable jobs. 3. C++ code implementation. Explanation of the code *. Job struct * represents a job with its ID, profit, and deadline. Compare jobs function *. A comparison function used for sorting jobs based on their profit in descending order. stdsort uses this to order the jobs vector. Find max deadline function finds the maximum deadline among all jobs. This determines the size of the schedule array, which must accommodate all deadlines. Job sequencing function the core function that implements the greedy algorithm. Asterisk sorts the jobs using std sort and the compare jobs function. Asterisk determines the maximum deadline. Asterisk initializes the schedule vector, a Boolean array, to track whether a time slot is occupied. Asterisk iterates through the sorted jobs. For each job, it attempts to find a free slot from its deadline down to 1. Asterisk if a free slot is found, the job is scheduled, the schedule array is updated, and the profit is added to the total profit. Asterisk main function asterisk creates a sample set of jobs and calls the job sequencing function to find the optimal schedule and total profit. The result is printed to the console. How to compile and run asterisk. 1. Save asterisk save the code as a .cpp file, example job_scheduling.cpp. 2. Compile asterisk use a C++ compiler, like G++, to compile the code. 3. Run asterisk execute the compiled program. Output asterisk. 4. Complexity analysis. Asterisk time complexity asterisk. Asterisk sorting the jobs, O, n log n, where n is the number of jobs. Asterisk the outer loop iterates through each job, n times. Asterisk the inner loop iterates from the deadline down to 1. In the worst case, this loop can iterate up to the maximum deadline, let's denote it as d. Asterisk therefore, the overall time complexity is O, n log n, plus O, n asterisk d. Asterisk in many cases, d is relatively small compared to n, so the time complexity can be approximated as O, n log n. However, if d is significantly larger than n, the O, n asterisk d, component becomes dominant. Asterisk space complexity asterisk. Asterisk O, d, for the schedule array, where d is the maximum deadline. This represents the space needed to track which time slots are occupied. Asterisk O, n, in the worst case for the schedule job its vector if all jobs can be scheduled. Asterisk overall, the space complexity is O, d plus n. 5. Optimization techniques and considerations. Asterisk disjoint set union, DSU, for time slot management asterisk. For larger values of d, using a simple Boolean array for scheduling becomes inefficient, especially if deadlines are clustered. The disjoint set union, DSU, data structure, also known as union find, can optimize the time slot management. The idea is to represent the available time slots using a DSU. Each time slot is initially in its own set. When a job needs to be scheduled by deadline X, find the available slot closest to X, using DSU's find operation. If found, schedule the job, and then union the slot with the next earlier slot to represent that the found slot and all subsequent earlier slots up to the previous available slot are now occupied. This approach significantly reduces the time complexity of finding available slots, especially when dealing with a large maximum deadline and scattered deadline values. However, this technique adds the complexity of implementing and understanding the DSU data structure. Asterisk choice of sorting algorithm asterisk. STD sort is generally a very efficient sorting algorithm, often implemented using intro sort, a hybrid of quick sort, heap sort, and insertion sort. However, if you have specific knowledge about the data, example profits are within a limited range, you might consider using counting sort or radix sort, which can achieve O, n, time complexity in those special cases. However, these algorithms may have increased space complexity. Asterisk edge cases asterisk. Asterisk empty set of jobs asterisk handle the case where the input jobs vector is empty. Asterisk jobs with deadline 0 or negative deadlines asterisk adjust your algorithm to handle or reject jobs with invalid deadlines, depending on the problem requirements. Asterisk duplicate job IDs. Asterisk if duplicate job IDs are possible, ensure your scheduling algorithm and output handle this correctly, example by keeping track of scheduled jobs using the job object rather than just the ID. 6. Alternative problem variations. Asterisk multiple machines. Asterisk a more complex variation involves scheduling jobs on multiple machines, each of which can only process one job at a time. Asterisk precedence constraints. Asterisk some jobs may have dependencies on others, example job A must be completed before job B can start. This adds significant complexity to the scheduling problem. Asterisk variable job durations. Asterisk instead of each job taking 1 unit of time, each job may have a different duration. This introduces the need for more sophisticated scheduling techniques. Asterisk minimizing completion time. Asterisk the objective may change to minimizing the average completion time of the jobs, rather than maximizing profit. 7. Conclusion. Job sequencing with deadlines is a classic optimization problem that demonstrates the power of greedy algorithms. By prioritizing jobs with higher profits and scheduling them as late as possible, we can find an optimal solution efficiently. Understanding the algorithm, its time and space complexity, and potential optimization techniques is crucial for solving this type of problem in various contexts, especially in algorithm design and resource management. Remember to consider the problem's constraints and variations when applying and adapting this algorithm in practice. The DSU optimization can be a valuable addition for large deadlines and scattered deadline values.